If you're here to learn a little bit more about landing gear systems, you've come to the right place. That's exactly what this video is for. Welcome back. So this video is going to talk about landing gear systems, not just the retractable type, which is really the focus of this week's discussion, but also a few of the other ones you might see out there, and how you can safely operate the gear and some of the equipment that's built in to help you not make the news. So of course our objectives and standards from our Jeppesen syllabus are to explain components and operation of retractable gear, talk about gear malfunctions, how to work the emergency gear extension system, and demonstrate an understanding of the system. A few references for this chapter. So the main one is going to be Chapter 11C of your Guided Flight Discovery Instrument Commercial Pilot textbook. That is where most of this information comes from. I also dive a little bit into the Airplane Flying Handbook, Chapter 8, which is the operations of, so what to do after landing, when to extend the gear. Chapter 11 is all about the systems themselves. Chapter 11 is titled Transitioning to Complex Airplanes, so they talk about the gear a lot there. The Pilot's Handbook of Aeronautical Knowledge, Chapter 7, refers to aircraft systems. And then the AMT Airframe Handbook, Volume 2, Chapter 13, is another useful reference. Basically, that's the handbook that airframe and power plant mechanics use during their training to learn how to maintain these systems. So there's a little bit of good useful information there too. And then, of course, I've got a handful of YouTube videos, which will be linked down below. And then the folks at boldmethod.com. I always get a good shout out because they have such good products for them. As of the filming of this video, they just released their Bold Method app, which is totally free. I highly recommend you go sign up for it. And the worst thing that's going to happen is you'll learn a little bit more each week. So let's talk about what we probably should already know, just to make sure though. We've got tricycle landing gear on the left. Think of riding a big wheels tricycle with the wheel in the nose. So you could call it nose wheel, but it's tricycle. And then conventional, think of the older aircraft, and they have a tail wheel aircraft. So conventional is tail wheel. A lot of newer pilots or the children of the Magenta line think this is conventional because this maybe is probably all you've ever flown, but tail wheel is conventional because it came first. So why should we have tricycle gear? Why should we have tail wheel or conventional gear? So tricycle landing gear, let's talk about the pluses and minuses of both first. Tricycle landing gear, some advantages of them. One, they allow more forceful application of the brakes without nosing the aircraft over. And a few things on this one. I'm obviously going to go down this rabbit hole. Are they brakes or are they brakes? Okay, so if you use the brakes improperly, you're going to break something. So why are you even using the brakes is really my question. You use the brakes when you do your run up. You use your brakes to stay stopped or to slow down after you've already slowed down. Yes, you use your brakes during a short field landing, but as we'll discuss, that's usually done wrong. And you just shouldn't. So basically, I go into Chapter 8 of the Airplane Flying Handbook, and here's what they say. During a normal landing, you only use the brakes after you slow down. You don't use them to slow down. So you aerodynamically brake, the aircraft will slow down. You've probably got a nice long runway in front of you. You don't need to make the first exit. So I like to use the brakes on a normal landing after you've slowed down. So you land, you maintain control of the aircraft decelerates, it's firmly on the ground, you maintain directional control, and then as you need to, you can move your feet up on the pedals and you can use the brakes. Don't slow the aircraft down with them. Okay, you're not flying a commercial airliner that has thrust reversers and max braking because they're bringing a 1,000,000-pound aircraft to a halt before the end of the runway. All right, you're flying a 2,000-pound 172. You don't need all that to stop it and slow it down. Now, during short field landings, you will need to actually practice putting your brakes on. And I say this because as a flight instructor, I have seen way too many commercial pilots, way too many flight instructor applicants who have never actually fully braked maximum braking on the aircraft before. And I'm not exaggerating when I say so many times I'm in there with somebody with a private pilot certificate who had to demonstrate proficiency in short field landings, somebody with a commercial pilot certificate going for their flight instructor certificate. And I say, all right, so I want to land on the numbers and I want to take the first taxiway. and it's 1,000 feet down there. It's more than easily. The 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 POH says you can land that aircraft at 600 feet of ground roll. So we have more than a 50% safety margin over what it says we need. And I'm going to say 9 out of 10 times the pilot lands and just stomps on the brake like it's in a car. Okay, your airplanes generally don't have anti-skid braking systems in them. So, and so the point I'm getting at here is make sure that you actually do it. I don't say every time you're going to wear out the tires and the brakes on these aircraft if you're using the brakes all the time. But at least some point in your training, you need to actually use the brakes to make sure you know how to use the brakes before you ever get put in the situation for real. Here's what happens on a tailwheel aircraft if you if you apply the brakes too abruptly. This will be linked down below for you. And basically, it's probably worth watching, so let's go ahead and do that. Okay, so we see Red Bull Racing aircraft here, conventional tailwheel. This is one of the disadvantages of a conventional aircraft, is that the nose is generally going to be a little bit higher, and which impairs your forward visibility during taxi. There's a few ways around this. You can kind of do S-turns down the taxiway. To exacerbate this problem, to make it worse, he's got a shorter canopy on there to make the aircraft just a little bit faster, so he can only sit up so far. And then let's not do it that way. And let's see what happens. He sees the aircraft too late, slams on the brakes, destroys his own propeller and his own engine to save the airplane who was parked right in front of him. So if you don't want that to be you, he didn't do anything wrong, I'll be honest with you. But that's one of the dangers that could happen in a tailwheel. If it was a nose wheel aircraft, honestly, he may have rear-ended the aircraft in front of him, but he probably would have seen him better, because in a nose wheel aircraft, you can see a whole lot better when you're taxiing. All right, here's what happens when, this is what happens all too often when pilots use the brakes improperly. All right, these things don't have anti-lock brakes. They generally will not have anti-skid brakes. If you push the brakes too hard, they lock up, and they only unlock if you let go. And it's really hard for your flight instructor to get you to get off the brakes, because I can't unclench your thighs that you're trying to push the pedals through the firewall with. So you need to be very cognizant, pay close attention to not tensing up your legs and not getting on the brakes too much. I will say one of the things you need to do is not have your feet on the brakes at all when you come into land. Have your heels on the carpet, have the balls of your feet on the rudder pedals, and that will, even if you do tense up a little bit, you won't accidentally use the brakes because you're not touching the brake pedals. It's really disheartening to see, brand new-ish tires that have flat spots on them. These are pretty egregious there. These landed with the brakes locked is what happened over here. You've got a lot of tread life, a lot of life left in this tire, but now it's worn all the way through to the cords because somebody locked up the brakes on it. So how are you supposed to use the brakes? Here's what the Airplane Flying Handbook says. As the airplane settles, the proper landing attitude is attained by application of whatever back elevator pressure is necessary. In other words, when you land, main wheels first, nose wheel in the air, because we're talking about tricycle gear aircraft. As the aircraft slows down, it wants to nose down, and it wants to put the nose wheel back on the ground. The Airplane Flying Handbook says that you should keep applying back pressure to try to keep that nose wheel in the air. All right, it looks cool. It's better on the nose wheel. And it helps slow the aircraft down because now you've got wings and elevators and the whole fuselage is slowing the aircraft down. After the main wheels make contact, you're supposed to apply that back elevator pressure to maintain a positive angle of attack for aerodynamic braking is what we're talking about, and to hold the nose wheel off the ground. Okay, this isn't me making this up. This is what the Airplane Flying Handbook says because this is how they want you to do it. And then they actually do talk about the brakes. They say careful application, not slamming on them, not stepping on them, is initiated only after the nose wheel is on the ground and directional control is established. So generally the way I land is I land on the mains and I keep my back pressure. I try to keep that nose wheel off the runway as long as possible. Eventually you have full up elevator. The nose wheel drops to the ground anyway. Make sure that you have directional control maintained, and then and only then can you worry about moving your feet up the pedals and applying the brakes. Nice and softly. And that's only if you need to, folks, okay? I'm not saying you have to use the brakes. Slow down first before you use them is what I'm basically begging for right here. Okay, so with the tricycle gear, you can use the brakes harder without tipping the aircraft over. We already saw an example of that. They give you better visibility during takeoff, landing, and taxiing. And you saw that in the video as well. And kind of here's your, in a tailwheel aircraft, you'd have to have the tail wheel up quite a ways to be able to see over the nose of the aircraft. And you saw in the video he couldn't see around the nose until he was too close to the airplane, didn't see it in time. Or in a tricycle gear aircraft, you can see over the nose a whole lot better. Better forward visibility during taxi, takeoff, and landing. And then finally, the last advantage of a tricycle landing gear is you honestly can be a little lazy with them. You don't have as much of a danger of ground looping happening to you in a tricycle gear aircraft because of where the center of gravity is located in relation to the main wheels. In a tricycle gear aircraft, the center of gravity is in front of the main wheels. That makes it sit on the nose wheel. Or in a conventional gear aircraft, the center of gravity is behind the main wheels, which helps it sit on the tail wheel. Well, basically, if you land a nose wheel aircraft, you're not quite aligned with the runway. And as it decelerates because it kind of lurched onto the runway, the center of gravity being forward of the wheels keeps the center of gravity forward of the wheels. It helps put the nose wheel on the ground, helps keep it pointed where it is. Well, on a tailwheel aircraft, if you land and you're not quite aligned with the runway, if your center of gravity then, as the aircraft decelerates from that lurching onto the runway, the center of gravity tends to want to go in front of the main wheels. And it does that by turning the aircraft around. Here's kind of a little, so what is ground looping, you might ask? That's a great question. It's not something you want to be a part of. At least it's embarrassing. At most, you're going to ruin an aircraft. A couple definitions of it from the Airplane Flying Handbook are an uncontrolled turn during ground operations that may occur during taxi takeoff or during the after landing roll. It's most common during the after landing roll. A sharp, uncontrolled change of direction on the ground. And because this picture doesn't do us all that much justice, let's see what a ground loop looks like. More common with tailwheel aircraft, it's generally going to, it doesn't mean that you're always going to drag a wingtip, it just usually happens that way. It's pretty hard on the landing gear, it'll pop tires off beads, and a lot of times the aircraft will nose over and hit propeller into the ground and cause some other maintenance to need to be performed. So as we see, here's another ground loop coming our way. We see as it slowed down, the center of gravity tried going in front of the main wheels. Here's what it was trying to do. This beautiful Stearman or an SNJ. As long as the aircraft is pointed the way it's going and it's going down the center of the runway and there's no lateral movement, the CG is happy being behind the main wheels and staying there. But once you see the aircraft starts to get a little out of control, you see it leaning on one wheel. The tailwheel down, you see it start to swerve now. And just one thing after that, once this thing starts to go, it's really hard to recover after that. The tail wheel is not doing a whole lot of good to help keep it pointed down the runway. It started going off the left side of the runway. You see the weight start to shift over here onto the right wheel. And now what's happening is the center of gravity, which is back here, is now trying to go in the direction they were going before, which means it's going to move the tail around the outside of the right wheel. And drag the wingtip, or lurches to a halt. And fortunately, this aircraft received very little damage. It popped the tire off the bead. It caused a little bit of deformation and some fabric damage, but it didn't damage the wing. The propeller never hit, so the engine's safe. It's going to at least go to fly another day. Again, it's pretty embarrassing. So my old man, who's a crop duster for 40 years, said there's two kinds of pilots, those who have and those that will. So it's your job to try to dispel that myth. Okay, if you don't want to ground loop, one way to do that is to fly nose wheel aircraft. Now that nose wheel on the tricycle gear aircraft, most of the time there's two different types of nose wheel control. Either steerable, which means when you move your rudder pedals or a steering tilly on larger turbine aircraft, then the nose wheel turns. And it's either by cables or bungee cords or rods, and I'm not kidding about bungee cords or springs. They help you turn quite a bit. So when you have a steerable nose wheel, you push the rudder pedal, and as the aircraft rolls, it tends to turn the wheel in the direction you want it to go, which means you don't have to use the brakes. Or differential braking is when you use one brake more than the other. The other type of nose wheel construction is castering, free castering. It swivels. It's not hooked up to anything. It's like the front wheel of a shopping cart. And regardless, it's very important that you understand this, as these books all say, you still taxi with your rudder pedals, no matter if you have a steerable nose wheel or a castering nose wheel. Because basically, here's what's going to happen. You're taxiing a steerable nose wheel, you push the rudder pedal, the nose wheel turns the direction you want to go, and you didn't have to use brakes at all. You're taxiing a castering nose wheel aircraft. You push the rudder pedal, nothing moves the nose wheel, but the rudder moves. The propeller wash over the rudder still moves the tail away from where you want the nose, so it still does what you want it to do. So primarily, you still taxi with rudder pedals no matter what. What you don't want to do is only use differential braking to taxi. So you can use differential braking when it's needed, okay, but it is not the primary way to control taxi direction. It's the Cirrus SR22, for example, has a free castering nose wheel. It's not connected to bungee cords or anything. They have a very bad habit of overheating the brakes, because specifically the right brake on most of the aircraft that you'll see, because students will drag the right brake to keep the aircraft from going off towards the left because of our left turning tendencies. Instead of applying full right rudder and then only using brake if they need to, too many pilots just drag the right brake. And if you got a mile-long taxi, you just drug the brake for a mile and heated up the brakes the entire time. That does two bad things. One, it wears the brakes out. Obviously, they need replaced. You see the right tire is usually more worn out than the left one as well, too. And finally, if the brakes, here's how the brakes work. The brakes turn motion into heat. That's how brakes work. They turn the kinetic motion of the wheel into heat on the brake pads, and that's what slows the aircraft down. Now, thanks to that, they can only turn so much into heat before they catch on fire. They just don't work anymore. The brakes start to get mushy, and then the brakes start to fade, and then the brakes don't work at all if they get too hot. So if you drag your right brake all the way to the run-up area, and then you take off, your brakes are already hot, and they might not work as well for you if you have to abort that takeoff. Or they might not work at all. Now, one of the Cirrus SR22s, for example, have brake overheat indicators on them. So if the little square inside them turns black, the brake has been overheated. It needs inspected prior to its next flight, and then a new sticker put on there. And I'm telling you, depending on where it's located on the airport surface, if you have a long taxi to the runway, these things go fast unless you're actually really careful and try to turn with your rudder pedals instead of just differential braking. Okay, so we talked a lot about tricycle gear aircraft. Now, what about conventional? What about our tailwheel aircraft? Why have them? What are some advantages and disadvantages of them? So we see here, this is an airplane single-engine land-equipped aircraft. It just happens to have skis on them as well. So this isn't a seaplane, even though it's on frozen water. This is a single-engine land aircraft. So we have them because we have better ground clearance. So you end up with bigger engines, bigger propellers, without having to make the whole aircraft taller. And it's better for unimproved fields because the propeller is a little bit farther away from the runway. And they're lighter weight. Having a tailwheel all the way in the back of the aircraft is a lot easier to build and lighter in construction. There's less structural members that you need to build into the nose wheel for a nose wheel aircraft. So they're generally lighter. They usually have a lot more useful load compared to its compared to its conventional wheeled aircraft relatives. So the bad, though, is they're harder to control on the ground. You saw a couple examples of a ground loop. And another way of saying that is the CG tries to go ahead of the main gear. and you have reduced forward visibility during taxi, takeoff, and landing. It's actually enough of a difference and enough, and the difficulty is that much more that there's 6131 requires grounded flight training and an endorsement. That's the 6131 endorsements include high performance, complex, high altitude, tailwheel aircraft. If you want to know more about tailwheel aircraft, go ahead and look at the Airplane Flying Handbook, Chapter 13. I'll try to remember to link it down below too. Some other types of landing gear. So I diverge a little bit from the book on some of these because I want to cover more than just the chapter. I want to make sure you know when these aircraft fly over, you know what you're looking at. So tandem landing gear, like on a lot of gliders have tandem landing gear in the fuselage and the tail, and they may or may not even have wheels on the wingtips. So a lot of gliders actually need people to wing walk it, to hold the wing up so it doesn't drag the wing on the ground. B-52 has tandem gear. You see tandem gear on the AV-8B Harrier. And then once you start putting two wheels on one main landing gear, this is a dual main gear as opposed to a single nose wheel. It's got a dual main gear in the back, and then the outrigger wheels are both single wheels. So you put two wheels on one gear. It's called dual main gear. And then what if you want to put more than two wheels? They call them bogie landing gears. Here's an example of a triple bogie main landing gear on a 777, on a Boeing 777. So when more than two wheels are attached to the landing gear strut, they call them bogie. A double bogie if there was four wheels, or a triple bogie if there's six wheels in this example. Now we have shock absorbing landing gear, or non-shock absorbing, and it's done a few different ways. You see here in the J3 Cub, there's inside these boots, there's just a bunch of bungee cords. It's a pretty light aircraft. If you bang it on the ground hard enough, these bungee cords will give, and as you taxi down to unimproved areas, this gear bounces a little bit. That actually makes ground looping a little harder. Harder to stop once it starts. Once it starts to tilt towards that one wheel, it's going down a one-way road at that point in time. Moonies shock absorb by having the rubber, stacked rubber donuts basically, and that's where some of the shock absorbing comes from in Mooney type landing gear. There might also be air oil shock struts is a pretty common one, especially in the nose wheels of the Cessna 172s, most Cessnas, and in the all three landing gear of a lot of low-wing aircraft. All three wheels of the Pipers are air oil shock struts. There's a couple main types of them. This is out of the maintenance manual when they talk about how to maintain them and the parts of them. I'm not going to get into the weeds on this because if you see these parts of the shock strut, it's probably blown apart on you. That means you didn't treat it very well. But basically, there is an inner cylinder. This is the shiny chrome looking one that goes inside the outer cylinder. Inside there's a few parts that make it all work. There's a meter pin, so basically when it's fully extended, it moves easier. But when it starts to collapse more and more towards this completely compressed location, it gives more, it moves harder. It's harder to move. So usually there's nitrogen and hydraulic fluid that, so when serviced properly, will support the weight of that aircraft and that load. So air oil shock strut. Now, non-shock absorbing landing gear, you see rigid steel gear here on these old school aircraft. A very rough ride, and these only flew out of unimproved airfields because there wasn't such thing as paved airports back then. So it was really rough on the aircraft. Every bump and every pothole would go right through to the airframe, and everybody in it would feel it. In your training aircraft, like your 172s, it's a stainless steel tube that yields as it bends. This textbook refers to those as non-shock absorbing. Basically, the landing gear itself just absorbs some of the load so it doesn't impart dangerous forces onto the fuselage itself. So depending on who you talk to, they might say, hey, that stainless steel tube yields, that is shock absorbing. Well, no, it's not a bungee cord. It's not an aerofoil shock strut. It's a metal tube bending to absorb the shock isn't necessarily a shock absorber. Okay, it's metal yielding. Okay, so let's get into our complex part of this. Let's get into retractable landing gear. So we know this already because we talked about this when we talked about constant speed propellers. A complex aircraft is one that has retractable landing gear, flaps, and a controllable pitch propeller, and there's a whole bunch of other stuff with it too. So our LA-4 Lake Amphibian we're seeing here is a complex aircraft. It has flaps. They're actually hydraulically actuated. It has obviously landing gear because it's an amphibian aircraft. So this has main wheels that extend. They're hidden up inside the wing right here, right now, so they've popped down and out, and then a nose wheel is inside the hole as well too. This does not have wheels on the pontoons because it has two mains that are pretty spread widely apart on the wings, and then the nose wheel. Now, how can you fly a complex aircraft legally? You need the training for it. So again, 61.1 defines them as flaps, controllable pitch propeller, retractable landing gear. And 6131 is the endorsement that you need to act as PIC of a complex aircraft. And of course, it says you have to have ground training, flight training, and receive a one-time endorsement from an authorized instructor. Not just a buddy with a complex, it has to be a buddy with a complex and a CFI certificate. Okay, so why retractable landing gear then? Well, so some advantages, we have less drag. So we can go faster, we can go farther, we can climb better. Don't forget the most important one that's not even on here is you look way cooler with those retractable landing gear. Other advantages are added drag. So then we have a faster, sleeker aircraft, but now if we need to slow down or if we need to descend, we can put the landing gear down and add drag. Now, a lot of times, extended landing gear on a retractable gear aircraft cause way more drag than there would be on a smooth, regular fixed gear aircraft. That's because the recesses the wheels go into act like individual air brakes. The landing gear doors that are attached to the wheels or that open or close during the extension or retraction cycle all cause drag. And not only that, but the doors, especially if they're on the main wheels, act like vertical stabilizers that you might extend down below the aircraft. So extending the landing gear actually makes the aircraft more, increases the yaw stability of the aircraft as well too. Disadvantages of a retractable landing gear, there's actually quite a few, okay? So first of all is you have to put the landing gear down before you land. And that is apparently way harder than it sounds because, as we'll talk about, people land with the wheels up all the time. Retractable gear systems, way more because there's hydraulic pumps or electrical pumps and adjustable linkages and potentially gear doors and all the other equipment that it takes to move wheels up and down. And all that costs money as well as weights. And then you have to maintain the equipment. Every year you have to check the emergency extension system. And then occasionally you have to fix damages caused to the aircraft because some pilot forgot to put the wheels down. So it's a lot of responsibility. And because of that, we need to have the 6131 training and endorsement. This is an underneath view of a 737. So on the 737, the Boeing 737, this portion of what will be the lower wing is attached to the main landing gear. So when the main landing gear folds in, it's a very simple process. So you've got the drag links here, the wheels pull in, and they just sit inside the wheel well. So there's not a door that pops open over the wheels. If you go hang out here in San Diego, you go hang out at Point Loma, and these airplanes fly over you pretty much nonstop. You'll see as their gear comes up, you'll actually see a wheel right here. There's no door that covers it up. It's one more thing to break, one more thing to have to install and maintain. So instead, they just put a cool hubcap cover over the wheel, and it works good enough. Some other aircraft, specifically long-haul aircraft, the 787 and the A380s, and most of the Airbus series, they actually have a door here that opens up. The wheels go into it, and then the door closes on top of it to make it look like it never had wheels to begin with. Those are more complex, but they actually do give you a little bit more streamlined, less drag performance for those longer flights. And then we mentioned amphibious aircraft, but here's an example of a float plane. Really quick, seaplane. See, it's a boat hull. It looks like it was built primarily to land on the ocean or on the water, and then a float plane that has floats in place of where there could be fixed wheels. So there's a land version of this aircraft that has fixed landing gear and a nose wheel, and this is the float version of it. So amphibious, it can land on land or water, obviously.
Down to is you need to know your aircraft. Most of them have an electrical system or a hydraulic system or a combination of the two. We'll get more into that in a little bit. And just for an example, here's out of a Cessna 210 Centurion, I think. When the nose wheel is lifted during takeoff, the gear motor starts to run, or might start to run up 2 to 3 seconds. Depends how long it sits, depends how good the system is. Basically, there's a low pressure switch and a high pressure switch that try to keep the hydraulic pressure in between a low and a high pressure. The pump can't run on the ground, even if it's low on pressure, because there's a safety switch on the nose wheel that prevents the motor from running. But when you lift the nose wheel for takeoff, it extends the nose strut, the safety switch closes, which lets the aircraft think that it's in the air, even though it's not in the air yet, and it lets that pump run. So hopefully your gear handle's in the down position where it's supposed to be when that happens. Because yes, if you put the handle up on the ground, nothing's supposed to happen, but during the takeoff roll, the gear might start to retract prematurely. Another key thing to know about this aircraft is the way the Cessna main landing gear folds back into the fuselage. You need to make sure that you use the brakes to stop the wheels before you retract the landing gear into the fuselage. Otherwise, they might not go in at the right angle because of gyroscopic precession. So let's talk about some nomenclature on the landing gear. So the trunnion is the part of the main landing gear assembly that attaches to the fuselage. And then we've got a bearing surface here. This whole thing has to pivot to let the wheels come up into the engine nacelle or the fuselage or wing, and then let it go back down again. The drag strut is that component that drags it up into the wheel well, drags it into the aircraft, and drags it back down. And then some kind of retracting mechanism. We'll get into that. Here's a wheel that folds inward, usually, not always, but inward, and folds up into the fuselage or the wing. We have landing gear doors on the outside of this one, so those gear doors come up and down. We saw that in the 737 earlier. And we've got a lot of the same nomenclature. You see this includes some brake lines on there, the axle that the wheel goes onto. You got your brakes down there. This is a shock strut. And what I really like about this one is we get a side view of the downlock and of the drag strut. This one's a side strut because it pulls it in towards the side. And here's your whole retracting mechanism up here. There's usually a spring that holds the downlock in place. And let's talk about how this works first. So basically, let's say when all this pulls up, it's going to pull up the side strut, and as the whole side strut and the retracting mechanism goes up, the wheel's going to then fall sideways up into the fuselage. Now, what we really need to know is it's not just hydraulic pressure that holds the wheels down, because what if you have a leak and you lose all the hydraulic fluid, then it would just fold up on you. It'd be pretty embarrassing. So when the gear's down, there's actually a down lock. This is a component that's holding the gear down. On the side strut here, usually what happens is they'll be extended straight or slightly over straight. Like you straighten your arm and you locked your elbow out, and that's what the side strut or the drag strut does here. So the down lock is a mechanical lock that holds the side strut or the drag strut extended to keep the gear down. So it's not magic, it's not hydraulic fluid or electrical current that holds the wheels down. It's a physical lock that does it. It's really important with the emergency gear extension systems, because you'll know if you need what it takes to get a positive locking mechanism to get the wheel down and locked. So here's the nose strut on like a 172. It's a air-oil shock strut. The torque links is what we're looking at here, obviously, are to keep the the bottom part of the strut aligned with the top part of the strut, and that's really all they do. And we call them scissors also, but they'll hinge right here on the point to let the shock strut go in and out, but then everything keeps lining up like it's supposed to. And on the RG aircraft, this is where the safety switch is, because there's not really a good place to put it on the main wheel. So, and these are the forks that you put the wheel into. Now, it's really important when retractable landing gear, nose wheel specifically, because usually the mains don't turn, usually, because there's applications where they do, but usually it's the nose wheel that turns in these tricycle gear aircraft, and you want to make sure that it retracts, that it's straight when it retracts. The recesses these landing gear go into generally aren't that much bigger than the tire, so it's really important it comes up straight. And one way of doing that is by having a centering cam inside of it. This is not something you can see and you can pre-flight, but know that you should have that wheel straight when you take off, and if it's not quite straight, then there's a centering cam inside the strut that does it for you. Probably more applicable to helicopters who could stop and have the wheel crooked when they take off, and as I've actually had that happen in the military, and we had to break a few components to get things safe on the ground again. So the centering cam works unless the wheel's too crooked when you take off. Finally, the shimmy damper. It does exactly that. It dampens the shimmy. So a few things. You go down the takeoff roll, and you start to feel like a shimmy, like it'd be the front wheel of a shopping cart if it didn't have the shimmy damper on there. The angle the nose wheel's mounted, the amount of weight you're putting onto it, it's a lot to ask for that poor little nose wheel. So I really ask you to be nice to it. Like ideally, when you do your takeoff roll, you don't have full elevator down, shoving this nose wheel into the ground and getting the propeller close to it. So a good general habit is to kind of put a bit of a neutral elevator as you apply the throttle for your takeoff. That way you're not shoving the nose down. You're more kind of a neutral buoyancy, if you want to think of it that way. You're not putting any extra weight on the nose wheel. And it will thank you for it. These things do go bad. They get really old. They get really abused in flight training aircraft, so be kind of nice to them. And then after you come in and land, you should be landing on the main wheels and keeping that nose wheel off as long as possible, because you're trying to keep weight off that nose wheel. Trying not to make that shimmy damper work too hard. All right, so the first of the three types, we'll talk about electrical gear systems. Usually it has one, like in your Beach Bonanzas, Debonairs, Beach Duchesses, you'll have one electrical motor, and it'll be connected to all three landing gear via these idlers and push rods. And so the motor runs in one direction, and all three wheels come up. It runs in the opposite direction, and all three wheels go down. And then we call that one gear cycle, retraction and extension of the gear. A few things about the gear: make sure you're not reversing direction mid-cycle. So don't bring the gear halfway up and then say, oh, 4-letter expletive, I need to bring the gear down again. You kind of got to let it come all the way up first before you reverse it. And the other thing is, this is usually where you get to with an emergency hand crank, which we're kind of trying to show you here. So it's somewhat easily accessible in the twin-engine Cessnas. It's underneath one of the pilot seats, and there's a special hand crank. You got to make sure it's there before you take off. You can't just like stick a crescent hammer in there and make it work. All right. And then just another close-up. So we got a little geared motor here, and usually there's some kind of a gearbox because you're trying to make it easier for the motor to do its job without pulling too much electrical current from the system. And then otherwise it's pretty zoomed in on the portion, but we've got our drag strut here, we've got our hinge point, and then the gearbox here would bring the gear up through all the bell crank mechanisms. Okay, hydraulic gear systems are generally going to be a lot more complex. Electrical gear systems are heavy. The gear motor's heavy. You got to have definitely some battery power to help out with it. Hydraulic gear systems can go farther. They can provide a lot more power, and for a lot longer period of time, basically, before you deplete your electrical reserves. So you get higher pressures from them. They're a lot more complex, a lot more chances for things to go wrong. Uh, so, for example, we'll go through some of the nomenclatures. A sequence valve makes sure that one thing happens before something else does. For example, before you bring the wheels up, you need to make sure you open up the gear doors. So, there'd be a sequence valve that doesn't let the landing gear retract until the gear doors are open. When we talk about the piston that moves your landing gear, we call it a cylinder. It's a hydraulic cylinder, or it's a piston, or it's an actuator. 3 different names for the same thing, but that's the usually shiny chrome part that's going to go through a seal into a larger housing, and a hydraulic pressure moves that one way or the other. Pressure switches usually have a high pressure switch so the pump knows when to shut off, or a low pressure switch so it knows it needs to turn the pump on, or some way to keep pressure between those 2 values. The reservoir is just where that fluid is stored. Usually there's plenty of fluid that'll fit in the lines. We bleed all the air out of them, and then plus extra. Need to know where this reservoir is and know how to pre-flood it to make sure there's enough in it. These systems do leak, and so they will need checked periodically. And then the hydraulic pumps, you've got a couple options for those. You can actually just mount one onto the engine, so every time the engine rotates, it's moving a lever or a vane or something that makes hydraulic pressure. So those mechanical hydraulic pumps. Or you can have an electro-hydraulic system, and that's what we're looking at here. We have an electrical motor that pumps hydraulic fluid. That's the electro-hydraulic. A little closer view on this one. This is something like you'd see in a PA-28 Cherokee Arrow, a Piper Arrow, or a Piper Seneca or something like that, with a manual freefall emergency extension, which we'll talk about in a little bit. So just to show us a few more parts of the electro-hydraulic system, you've got your gear type pump here. It'll turn one way or it'll turn the other way, and fluid will move one direction or the other. A check valve keeps fluid from going the wrong direction. So in this system, you put the wheels up, and then there's no up lock that keeps the wheels locked in the up position. It's just hydraulic fluid that keeps them in the up position. And so the check valve, which is a little spring-loaded like ball valve, that keeps the fluid from going back through the lines from the weight of the wheels. Until you want that to happen, obviously. And let's see, shuttle valves just determine if the fluid's going to go one way or the other. Shuttle it back and forth. Our actuators, our pistons, or our cylinders. And so basically, you move fluid through the red lines, and it would lower the landing gear. Or you move fluid through the blue lines, and it would raise the landing gear. Think of the piston here. Think of a wheel down on the end of this. If you want the wheel to go down, you put fluid in this cylinder, and it pushes the piston down. If you want the wheel to come up, you put fluid into this part of the piston, and the whole thing comes up, and the wheel comes up. The freefall valve, which again we'll talk about more in a second, but this is a type of emergency extension for these systems. Since there's no uplock, there's nothing holding the wheels up except hydraulic pressure. Literally all you have to do is release the hydraulic pressure for the wheels to come down. You don't do that by introducing air into the system, because then it would take a lot of maintenance to get it flying again. So what we do then is you would open up the freefall valve on this type of system. What all that does is let fluid go from one side of the piston to the other, and the weight of the wheels pulls the piston down, and voila, gear's down. You didn't need hydraulic power. If you had a hydraulic leak and all the hydraulic fluid fell out, the gear would come down on its own. Pretty easy system. And then it gets a lot more complex. Okay, this is a simple large aircraft hydraulic gear retraction system. And really all we've added onto this one, we still have the same stuff. We've got some reservoirs that are off screen, but you've got your landing gear actuators, and all we've added in here is up locks. So this actually has a mechanical lock that holds the wheel up. In a very big heavy aircraft, a very big heavy landing gear, you'd blow all your hydraulic lines up just by holding the heavy landing gear up. So instead, the hydraulic system raises the landing gear, and then there's a mechanical lock that keeps it in the up position. Just for emergency extension purposes, there's usually some kind of a high pressure air that would then disengage the lock and let the wheel fall down on its own. Of course, the down lock we talked about before. And then here's the sequence valve we were talking about. So in this system here, there's a gear door actuator. So the gear door would have to open first, and then the sequence valve would open, and then it would let the landing gear come up. And once the landing gear is up, it closes the sequence valve, and the gear door closes behind the wheels. So these systems get really complex really fast once you start getting bigger. So again, learn the aircraft that you're flying. Okay, you ever see these remove before flight flags on an airplane flying around? Somebody probably messed up. Because you guessed it, you're supposed to remove them before flight. This is showing us ground pin or gear pin locks. This is mechanical pin lock here that keeps the down lock from coming out. You see the red pin here, you'd have to push the button and pull it out. There are times where we've flown with these installed intentionally, usually because something was wrong with the gear and you'd rather get stuck in the down position than the up position. But if everything's working like it's supposed to be, they shouldn't be there. So you can, because you can't retract the landing gear if they are. How do you know the gear's down? How do you know the gear's up? Well, again, it really depends on the system. So let's look over here first. Most gear handles are wheel-shaped. Okay, most flap handles are airfoil shaped or flap-shaped. And if you're flying an old GA complex trainer type aircraft, you probably have these kind of lights in there. I like this because it's just a light bulb that's inside there. They're all interchangeable. Let's say you go fly someday and you put the gear handle down, you get a green light, and no light. Well, a few things happen. It could be a bad light bulb, it could be a bad landing gear, or the gear's down and locked, and you just have a bad indication code to it, maybe a broken wire. You don't know. So what you can do is you can actually unscrew the one next to it and swap the bulbs out. If I'm looking for 3 ground to make sure I have 3 down landing gear, I'd probably pull the bulb out of the red one, which is a gear unsafe light. I don't want to see if it's unsafe. I want to know if it's down. If I have 3 lights, 3 green lights, this one won't be illuminated anyway. And then these also, you rotate it clockwise and it dims it. You rotate it counterclockwise and little cat eyes open up and it make it brighter. So one of the things you'll look for is to make sure the little cat eye shutters inside there isn't closed all the way. It'd be really nice if you had a green light for each wheel, so you can have this comfortable feeling that each wheel is down and locked. This light is actuated by a switch that's connected usually to the down lock. So when you have a green light, not only do you know the wheel is down, but you know the down lock is in place, so it will stay down. If you didn't have electrical power, or if you didn't have a green light, you might fly by the tower and they might tell you your wheels appear to be down, but you actually don't know if they are or not. Without a green light indication telling you the gear is down and locked, you just know it's down. You don't know that it'll stay that way or not. Now it depends on the type of system. So you'll see this in like a PA-28. I'll show you a picture here in just a second. The one green light for each wheel lets you know they're all 3 down and locked. The Cessna Cutlass system and the Cardinals will have a gear up light and a gear down light. So when all 3 wheels are down and locked, you'll have 1 green light. The problem with this one is if you don't have a green light, you don't know which of the 3 wheels it is. And then a gear up light is not green because it's not a great thing, because you don't want to land with the gear up. You can, we'll see videos of that. But it's letting you know that the gear is up. It's not a bad thing, but it's saying caution. That's what the yellow light means. Don't forget to put me down. Okay, the PA-28 Arrow has a gear unsafe light right smack in front of the pilot. It's even higher than the attitude indicator. Really hard to ignore. Basically, the way the gear unsafe light works is if the landing gear is not in the same position as the handle, the gear is unsafe. So, for example, if you take off, positive rate of climb, no runway remaining, you put the landing gear handle up, it takes like 5 to 8 seconds for the gear to retract. So for 5 to 8 seconds, it's not safe because it's not up or down. And then once the gear unsafe light, you'll feel it thump into the airfoil. The gear unsafe light goes out. You look down, you'd see a gear up indication on the yellow light or amber light. You come into land, you put the gear handle down. It takes 5 to 8 seconds for the gear to extend. So for 5 to 8 seconds, you'll see the gear's unsafe because the landing gear doesn't agree with where the handle is. Once you feel the thumps, you get 3 green lights. The unsafe light goes out. Now, a lot of these systems have a gear warning horn. Now, the gear warning horn is letting you know that the gear is unsafe. It means a few things depending on the manufacturer. Usually it means that you're configured for landing, but the gear's not safe, meaning it doesn't have a downlock indication because of a wire or because of a mechanical malfunction. Or it could mean the gear's not down and your flaps have extended past a certain point, or your throttle has been pulled to a certain point. In other words, you're doing some act that you would do to land, and the gear's not down. And it's pretty hard to ignore. Like it's annoying. Let's check it out and see. It is an annoying sound, right? And you might think, how could you ignore that? How could you forget that? Well, you just, and this is in a looks like probably in a 172 RG type aircraft. And I've heard that sound plenty of times. We test it. We could do a couple maneuvers where the horn is on. Just don't desensitize yourself to this. In case you don't know, this is not how a normal landing is supposed to sound. Yep, and he said, "Gall darn it." Okay, so how could you ignore that? Well, it happens all the time. So that's a great question. So that one of the ways we prevent that from happening is from safety switches. They got a whole bunch of names too. You'll hear them called the WOW switch, which stands for weight on wheels, the scissor switch because these act like scissors and they'll chop your finger right off, or a squat switch because when the aircraft is squatted down on the ground, the landing gear is compressed and the squat switch is opened up. So the way this system works is as the landing gear extends, this little part of the scissors would then press up against the micro switch, and now you know the gear is extended. Not so much now you know, but now the gear retraction system knows the gear is extended. So this should theoretically keep you from retracting the landing gear while you're on the ground. It should theoretically do that. It does a pretty good job of doing that. So most airplanes, you go out there, you put the landing gear handle up, you power on the aircraft, the gear's not going to retract because this kept you from doing it. However, there are certain maintenance actions that you might need to disconnect them for. There are just normal movement to the aircraft on the surface, and your landing gear can extend enough to where the aircraft thinks it's flying and try to retract the landing gear. On like Cessna Cardinal and 182 RG type aircraft, this squat switch is in the nose. So literally you could power on the aircraft. It's an electro-hydraulic system. You could put the gear handle up and nothing will happen, but you go back and push down on the tail and the thing will fold up on the ground and just retract the landing gear on the ground. Kind of turns into a transformer. So you don't want that to happen, right? So you manually pre-flight this to make sure it's not broken, and it won't let you retract or extend the landing gear if it's not working properly anyway, depending on what the problem is. And then a couple of the ways. We talked about the throttle switch. So some aircraft, what you just heard on the horn on the video was the throttle was pulled back past usually around 15 inches of manifold pressure, and that causes the horn to go off unless the gear's down. So if you hear that horrible sound, it means that you're pulling a whole lot of power back, like you're coming into land and the gear's not down. Some of the aircraft might have an airspeed switch, like some versions of the Piper Aero 3, the PA-28R201, has its own little pitot tube for the landing gear system, and it won't let you retract the landing gear unless you've built up enough speed in its own pitot tube. And the older they get, the more out of calibration they get. I flew an Aero not too long ago, and you could not retract the landing gear until you were going like at least 95 knots, which is a little out of adjustment for where it's supposed to be, but there's worse problems than not being able to bring the gear up too soon. Okay, so when do you pull the landing gear up? Well, the right way to do it is from the airplane flying handbook, and they say normally retract the gear after liftoff, not before. When the airplane has reached an altitude where, in the event of an engine failure or other emergency requiring an aborted takeoff, the airplane could no longer be landed on the runway. All right, that's a mouthful. In other words, you don't pull the gear up if you could still use it to land on the runway. If you could still land on the runway, then your gear should be down. The second that you cannot land on the runway any longer, your gear should be up. Your gear being up helps your climb performance. It looks cooler, so you want it up, but don't do it too soon. And then I cut and paste from a few other different places, all right, from a few other POHs that talks about that. Now, the 172, the Cessna single engine series of retractable gear, the landing gear goes down as it retracts, about 2 feet worth. So make sure that you're at least 2 feet in the air before you retract the landing gear. And then just different aircraft are different. And then don't pull it up too soon. Here's a jet. I don't know if they had the handle up, but anyway, you see when the aircraft starts to rotate, what it did was it extended the struts. Now the aircraft thinks it's flying, but it's not actually flying yet. So it begins the retraction process, and they never actually got to leave the ground. So don't pull the gear up too soon, folks. You might make one of my videos someday. So we've got a couple V-speeds, new V-speeds we need to worry about here. So we talked about when to retract it, not until 2 things have actually happened. Not until you have a positive rate of climb and you're out of runway remaining for landing. And that might kind of sound like a tongue twister, but you need to practice it because you're going to say it every time you take off. No runway remaining, positive rate of climb, gear's coming up. I actually go so far as to point at my VSI and point out the window when I retract the landing gear. If it's icy or slushy, you just need to cycle the gear up or down a couple times. It'll knock off all the ice and the moisture. What you don't want to do is have a bunch of water on your landing gear, retract them into your wheel well, and have them freeze there and not be able to come back down again. There's an old version of the question that said you should leave the gear down for a while, but then they had landing gear freeze in the down position. It wouldn't come up. So just bring it up and down a couple times while it's still wet to knock off as much moisture as you can. We actually have 2 VLO speeds. VLO stands for landing gear operating speed. You see gear upper, gear up, and gear down. Okay, so these are 2 different VLO speeds. So to bring the landing gear up, you have to be below 107 knots. This is in a BA-28R. To bring the gear down, there's a VLO extend speed, which is 129 knots. When to extend, the best answer is before you land, and we'll get into that more later on. So VLO is actually 2 different VLO speeds, gear up VLO and a gear down VLO, one for extend, one for retract. VLE is your landing gear extended speed. So this is as fast as you can go with the gear down. This airplane can go a whole lot faster than 129 knots, but it's limited to that if the landing gear is down. If you want to go faster than 129 knots, you have to make sure you slow down below 107, bring the landing gear up, and then you can go faster than 129, up to your VNE speed, your never exceed speed. Here's out of probably a Cessna 210. I think I used them a lot in this one. Look, you can actually bring the gear up at 165, but you can put the gear down as high as 203 knots. I think that's also the VLO extend speed. No, I'm sorry. No, this one's gear operated. You can bring it up or down below 165, but you can't go faster than 203 with the gear already down. It usually has to do with the aerodynamic forces on the nose wheel, on the nose gear door itself. All right, so here's a good pre-landing check that you need to know by heart very well before you start flying complex aircraft. A lot of you might be doing some form of a GUMP check when you're flying your fixed prop, fixed gear aircraft. I personally don't teach my students a GUMPS check on a single fixed simple aircraft because too many of the GUMPS items you don't do. And I don't want you to skip GUMPS items because someday you're going to fly an aircraft that you can't afford to skip the stuff. But whatever. Some of you might be doing this, some of you might not, is the point. Once you start flying complex aircraft, you're going to be doing it a whole lot, like 3 times in each landing. So what BC GUMPS, I've added obviously quite a few letters onto this one because of my couple years of instruction doing this. Um, Depending on your aircraft, so if you're flying a low-wing aircraft like a Piper, um, you need the boost pump on for takeoff and for landing. If you're flying high-wing aircraft, most POHs don't require that. C, carb heat. If you have a carbureted aircraft, you need to pull the carb heat on. That should be on before you come in and land. Gas should be in the both setting if you have both, or in the fullest tank if you don't. So if you don't know, most high-wing aircraft have a both selection. And most low-wing aircraft, you can choose either left or right, or inboard, outboard, left, right, depending how complex they are. U stands for undercarriage, down and locked and verified. Okay, really important here, not just the handles in the down position. Many times in my career, if I put the handle down and the gear actually didn't come down, something was wrong. And you have to go troubleshoot it or figure out what's wrong. But just because the handle's down doesn't mean the gear's actually down. So generally what you do is you look at your green lights and you make sure that your green lights stay down and locked. And if you can, you want to visually verify it as well. A lot of aircraft will have a mirror on the wing or the engine nacelle, and you can actually physically see your landing gear in the mirror. Your prop needs to be full forward, but not too soon. Okay, I'm not talking like you're at 10,000 feet and you start, well, let's talk about landing, folks. You don't slam the prop full forward. You've used your prop control to reduce your RPM for better cruise performance and make a whole lot less noise. Don't undo that too soon. Generally, I won't go full forward on the prop, I'll be honest with you, until I'm base or final, because anything earlier than that, the prop's going to surge to a high RPM and make a ton of noise for people. And if you haven't picked up on this, people who live around airports don't like airplane noise. So try to keep it a little bit to a dull roar. Flaps, you'll get in the habit of checking your airspeed before you extend your gear. You should get in the habit of checking your airspeed before you extend your flaps. And it's just going to become more important the more complex aircraft you fly, because they might have different speeds for different flap settings. But you do want your flaps down as needed or as required. Okay, heavy crosswind, maybe you don't want full flaps. Short runway, you do want full flaps. Seatbelts and switches. So that's my S and my S. I double check and make sure everybody's belted in. You land one time with somebody whose seatbelt wasn't clipped in. Usually they didn't realize that it accidentally came off. So I have a habit of double checking seatbelts a lot. And seats and seatbelts, make sure their seats are upright and the tray tables are locked. And then switches, that's kind of one final. Are my landing lights on? Kind of check there. And then I actually usually will do, if nothing else, at least one last short final. Gear is checked. Okay, so I check my landing gear a lot when I come in, and for every landing basically. So when do you extend the landing gear? Honestly, the best answer is before you land. And I put duh, but different situations require different times. So out of the airplane flying handbook, they say normally the landing gear is extended and the before landing checklist completed prior to reaching the base leg. Now that is actually a great way to do that, because you're on downwind, your gear is probably not down yet. You beam your numbers, you start your gear extension process, and you start running some flaps and some other items and telling everybody this is, to get their cameras out, it's going to be the best landing ever. And you're still, too fast maybe for full prop or things like that. But you shouldn't really go past the base leg until your landing gear's down, until you're set. So I start doing a gumps on downwind. You might not be able to get through them all the way because you're then transitioning from downwind to base. The gear's in transit. You're still kind of reconfiguring the aircraft. But base leg on, you need to have pretty much your full gumps check done. The hole in this theory is, what if you don't have a base leg? What if you did a straight in approach? Then if you went off of this mantra, when I'm downwind to base, I'm going to lower the gear and do my gumps check, you would never do a gumps check. You would just do a straight in and land crashing on the runway. So the really best way that you can do a gumps check, I love our folks at Bold Method here, but I wanted to make one correction here. So this isn't the upwind leg of the traffic pattern, right? Because it's the departure leg of the traffic pattern. The upwind's over here somewhere, parallel to it. But anyway, so I will personally do if I do a traffic pattern, I do a GUMPS check here when I'm on the downwind. Some of the things might not be completed, like the undercarriage hasn't been fully down and locked yet, or but you should have the gas in the fullest tank. You should have your boost pump on, your carb heat on. You could have your mixture full rich. I wouldn't go full forward on the prop just yet because it'd make too much noise if you did. Seatbelts and switches should all be set. I turn on my base leg here. Okay, we'll double check. The boost pump's still on, carb heat's still on, gas is still on both. Undercarriage is now down, locked, and verified with green lights, and I verify in the mirror. Mixture's full rich or best power depending on your altitude. Prop is full forward because I'm going slow enough now. It's not going to make a whole bunch of noise. And then flaps are down to my next setting. And then switches, seatbelts, and seats all set. I turn to final, and you guessed it. Boost pump still on, carb heat still on. Gas is still in the fullest tank. Undercarriage is down, locked, and verified at least one more time. Mixture proper, full forward. Flaps are probably full by now, or your final flap approach setting. Switches and seat belts are still all set. You good on the right seat? Yeah, I'm good, thanks. And then if you have time, and when I'm on short final, I'll do like one more final gear check. All right, I had a flight instructor in the past that would mess with you on short final and like raise the gear or pop off a circuit breaker and stuff to see if you caught it before you landed, which I would not recommend. It's kind of dangerous. If I'm doing a straight in landing, you don't have a downwind or a base. So what I do then is I do, depending how fast the airplane is, 3 mile final is downwind, 2 mile final is base, 1 mile final is final. That pretty much gives you the same amount of time that you had in a traffic pattern. That's pretty close to the dimensions you're flying here. If you're flying a really fast airplane, though, that doesn't give you enough time. So do 5 mile, 3 mile, 1 mile. All right. Airspeed limitations. Your V-speeds become a little more complex with these aircraft because you've got a lot more options. You've got your speeds with gear up, gear down. You've got a best rate of climb speed, gear up, gear down. You've got all your limitations here on extension and retraction. Out of a PA-28R201, this is a 200 horsepower Cherokee Aero with retractable gear. VFE is 103, and there's no like partial flap speed. It's 103 knots, you can put them all in. 104 knots, you can't. Like some Cessnas. 129 is the VLE, 107 is the VLO retract, and 129 is the VLO, I did it backwards, VLO extend, VLO retract, VLE. Basically, so when you're flying in the Aero, before you put your hand on the gear handle or before you put the gear handle down, you're going to say below 129, gear's coming down. Or below 107, gear's coming up. Or below 103, flaps coming out. Making sure you don't overspeed any of those things. And then to make it more complex, there's different VX and VY speeds with the gear up and the gear down. So let's talk about doing like a short field takeoff and a max performance climb in a PA-28R201. So you've got your gear down and your flaps up, your best angle of climb speed. So you'd want to climb out at 72 knots to outclimb that obstacle because you've got the gear down. Well, as soon as you can and you're out of runway remaining and you have a positive rate of climb, you then raise the landing gear. Your VX speed is now 78 knots. But then after you've cleared the obstacle, you need to climb out at VY speed. Now that your gear's up, your VY is 90 knots. As opposed to when you first take off and you're not doing a max performance climb to outclimb an obstacle, you would normally take off with your gear down, your flaps up, you climb at 78 knots. As soon as you raise up your landing gear, you climb at 90 knots because it changes your VY speeds. So again, learn the aircraft you're flying because it's going to be different for almost all of them. Well, what happens when you don't put the landing gear down? A lot of scraping. You already saw one. We're not going to get to see this one. Looks like it has been moved since I created this slide. But it's not going to be pretty. You already saw it from the inside. You can imagine how ugly it is from the outside. There'll probably be a few videos down below that'll link you to some silly stuff too if you want to watch. So let's talk about emergencies. What if things don't work right? So if you have a problem with your landing gear, the first thing you should do is leave. Don't be in the traffic pattern trying to troubleshoot a gear malfunction. All right, everybody is going to try to help you, and the only way they can help you is by talking to you, and that's just distracting you more from actually figuring out what the problem is. So if you're in the traffic pattern, you go to put the gear down, and the gear doesn't come down, leave the traffic pattern and go somewhere else and go figure it out. Break out the POH, take your time. If your gear won't come down and you're out of gas, you've got compounding problems, and I bet one of those two were probably your fault, but or both. Now, they also say that normal gear retraction time is about 8 seconds, and then they talk about what if your gear doesn't come up? Well, there's worse problems. If your gear doesn't come up, then you're stuck with having landing gear down. That's great. What I've actually had happen in the past, though, was we went to put the gear up, the gear didn't come up, we went to put the gear down, the gear wouldn't go down either. We actually had to, it was in a helicopter, thankfully, we actually had to physically move the nose wheel down into the locked position and then put one of those lock pins into it while hovering. And of course, it was over a Navy ship in the middle of the Indian Ocean, but that's a story for another day. There is a video out there of somebody in a car pulling a wheel down on a Bonanza, so some crazier things have happened. But a few things: know your aircraft before you fly that aircraft. All right, so in the air, when you have a gear malfunction problem, is the wrong time to start reading what to do if you have a gear malfunction. Take your time. You probably have more than enough fuel for this. What you don't want to do is land with the gear up after you've thought you've exhausted all your other options, and then only to slap yourself in the forehead and say, oh, I guess I probably should have checked the circuit breaker, which has also happened too. And generally, when people put the landing gear handle down, but the gear doesn't go down, a lot of times it's because of the circuit breaker. So know your emergency procedures, know your aircraft, use the POH, and in order to give you a chance to read the POH, you need to leave the traffic pattern, hopefully have somebody else or George, the autopilot, help you fly the aircraft while you do it. And in case I didn't mention it, you should take your time. I know I mentioned this right there, but don't get in such a hurry to land with the gear up. Fortunately, there's a few different ways to put the landing gear down if they fail to extend. Looks like we've got, here's the procedures for one type of an aircraft. They're telling you first, make sure your master's on. Make sure your landing gear and the gear pump, they're two separate circuit breakers, are both in. Reset them if you need to. This electro-hydraulic pump pulls a lot of current, so it'll overheat and it'll shut down. A burned out bulb can be replaced. Make sure you double check those dimming shutters. That's the little cat eyes on the bulbs. They're telling you some troubleshooting steps to take here. Worst case scenario, you've got the free fall valve here. So this is like you see in the PA-28, right in between the pilot, co-pilot seats. There is a little lever in the front. You pull up on this lever, and it's that bypass valve. It's the free fall valve. All it does is just let the landing gear fall down on their own. Unfortunately, if you have the landing gear handle up and you actuate the free fall valve, the pump's going to run to try to bring the gear up while gravity's trying to bring the gear down. So follow your procedures. In a PA-28R, you make sure the handle's down, and then eventually you'll pull the circuit breakers, and then you extend it manually. Why would you pull the circuit breakers if the gear's already down? Because you don't know what's wrong with the system, and you don't want it to try to raise the landing gear up right when you're touching down on the runway. The Cessna single piston gear extension system is going to be a single hydraulic pump here. So the Cessna system does need hydraulic fluid because those wheels have to come forward as they come down out of the fuselage into the airflow. To do that, you pull the handle forward, and then you're going to it's just a long pump handle at that point in time, like running the bottle jack to a tire jack or something like that. The other two we all already talked about. The free fall system, again, that's how it works now. So you pull the free fall valve, and all it does is let the weight of the wheels push the fluid from one side of the piston to the other. And then your electric hand cranks. Sometimes the handle's always built onto it, usually not, because when the motor turns, the handle turns, and what you don't want to do is raise the landing gear, have a big red handle sling around the cockpit, and start breaking people's ankles. And then on the aircraft that have uplocks, because the landing gear is so heavy, there's got to be some kind of a compressed gas, usually some kind of a nitrogen pressure or something that blows the uplock out to let the landing gear fall by gravity. In most aircraft, you need to like slightly wag the nose left or right, yaw it left or right in flight, and the wind catches those landing gear doors and pops the wheel down into the full down position. And then the mechanical down lock keeps it there. But again, know your system, know how it works. This aircraft takes about 6 seconds to extend the landing gear, 8 seconds to retract, 6 to put it down because gravity is helping the gear go down. And they give you a few things. What if the gear doesn't go down? Well, you should look at circuit breakers. You should look at your master switch. And then slow down and try it again. Okay, these wheels are trying to go down into the airflow. So don't be right at your limit of extension speed. Don't be right at your 129 in your aero when you're trying to lower the landing gear because you're making everything go into 129 knots of wind. You slow it down below 100 knots, the gear comes down a whole lot easier. This is out of the Turbo 210N Centurion. The manual pump, the emergency hand pump between the front seats, you pull it out and you just pump it up or down, and it's basically a hand pump that is moving fluid instead of the electric pump. They're doing the exact same thing. There's actually quite a few aircraft out there that you can pump the gear up or down with a hand pump. And then there's actually a procedure for what if everything else doesn't work and you still got to land with the landing gear up. Well, there's a procedure for that. It should be a last-ditch effort. Hopefully you've exhausted all other options of extending the landing gear before you give up and do this. That includes talking to mechanics on the phone or on the radio, going out and doing some like high G turns to try to get the gear to come down on its own. And so this is a last case scenario. This is on a Cessna piston single. They're talking about let the landing gear swing into the gear wells at touchdown. So if the gear's partially extended, if it's not all the way down and locked, that's oftentimes going to be worse for you. You don't want one or two wheels extended and one of them not. It'd be better to land with all three down or all three up in a lot of times. In this case, they want you actually putting the gear handle up and push the gear and gear pump circuit breakers in. That way it'll help pull the gear back into the wheel well when you land. It'll be less damage that way. Here's what it looks like when a retractable landing gear aircraft lands on the runway without the wheels being down. It does a surprisingly little amount of damage to the belly of the airframe of the airplane. It's going to damage the flaps if they're down. This is a complete engine teardown. It's going to do a sudden stoppage inspection on the crankshaft. I'm pretty sure this propeller is going to need replaced. But to the airframe itself, there's actually not too bad of damage and repair. It could be a whole lot worse. It's going to take some work before it goes flies, but it could be worse. And if you want to learn more about the retractable aircraft, you can open up the Airplane Flying Handbook, flip back to Chapter 11. It's all about transition to complex airplanes. This is where I've learned a little bit about the constant speed propellers, and this is where a lot of the when you extend and retract the gear and a lot of stuff about the gear system. If it wasn't in your Jeppesen book, it probably came out of this chapter. And that's pretty much it for landing gear. Okay, so we talked about the different types of landing gear systems, the different landing gear designs, different types of retractable landing gear systems and designs, and the safety systems that keep you from retracting the gear too soon or forgetting to extend the landing gear before you land. And then when you use it, when to retract the gear and when to extend it. Quick summary here. Make sure that you don't retract the landing gear until you have a positive rate of climb. I'm holding up one finger. And until you're out of runway remaining for landing. I'm holding up two fingers now. When do you extend the landing gear? Well, before you land. That's the best case scenario. And then usually it's going to be you'll start the gear extension process on downwind, or if you don't have a traffic pattern in a downwind, you'll do it on like a 5 or 3 mile final. There are times where you're going to extend the landing gear earlier than that. Because remember, landing gear, when you extend them, gives you drag. So if you're high or if you're fast and you need to slow down or if you need to lose altitude, you probably want to put the wheels out. These airplanes are generally faster. They go places faster. They pick up speed when they descend because they have less drag. So a lot of these aircraft, they will do one of two things. They will come down, they'll lose altitude, or they'll slow down, like if you're holding altitude and the power's back. Most of these aircraft won't do both. You can't come down and slow down at the same time, at least unless you put your landing gear out and you have all that drag. The thing is, once you do have the landing gear out, you have these big empty wheel wells where the landing gear used to be, which causes a whole lot of drag and helps you slow down. All right, so that's probably it for today. As you're kind of testing yourself, I'm not going to give you the answers to these right here, but before you go fly a complex aircraft, you need to know it. So these are some questions we talked about, some questions you need to know about your aircraft. Here's your Cessna 210 example. VLO is 165, VLE is 203. On your aircraft, how do you know the gear's down and locked? There's probably going to be one green light or three green lights or a series of green light indications that tells you it's down and locked. Some aircraft actually have a visual pin that you can see on top of the wing to let you know the down lock's in place or something like that. VLE, landing gear extended maximum speed. You see the 210, it's 203 knots. VLO, retract and extend. They might be two different speeds. Know how the gear warning horn works on your aircraft. So in the 177, it goes strictly off of throttle position. If it's supposed to be less than about 15 inches of manifold pressure, the horn starts going off. If the gear's not down. The only way to get that obnoxious horn to go away is to either give it more power, which makes it hard to land, or put the landing gear down. On some of the aircraft, it's a flat position. For instance, if the flap goes to 25 degrees and the gear's not down, the gear warning horn will sound. Because why else would you have 25 degrees of flaps in if you're not going to land? Some aircraft might have an airspeed switch. So once you're below 65 knots and your gear's not down, it's going to start beeping at you, or it's going to just automatically extend the gear for you. The squat switch, even if nothing's broke, that squat switch doesn't think you're squatting if you're not squatting. And that sounds silly, but let's say you're going on a rough landing or a rough runway, and just the normal bouncing through grassy ruts and stuff like that, over curbs or what, I don't know what you do when you taxi, but the normal bouncing of the aircraft might actually extend the strut enough to where the aircraft thinks that it's in the air and will attract the landing gear on the ground. So the squat switch system can be tricked. It's not foolproof. You cycle the gear up or down after you take off to make sure they won't freeze in that position. And then we just talked about how you extend the gear in an emergency. Most Piper systems are free fall. Most Cessna system single pistons are a hand pump. Beech twins and Cessna twins a lot of times have electric motors that you have a red handle you have to crank to get the wheels to go down. So it just depends on the type of aircraft you're flying. So really check the POH for your system, and of course check your Jeppesen book for the answers to these questions, because they do a better job answering them than I do. Okay, that is it, folks. So I hope you picked up something about landing gear systems along the way, and check on Canvas for assignments, and thanks for watching. We'll see you next week.